Alright.
Is the stack at the end of this?
Okay. The end of that? No, there's differential equations after that. Actually, yeah, we might be able to do it at the end of this, yes. So I don't think the differential equations bits on it. So yes, we might do that. Alright, so integral calculus is what we're looking at. So essentially it's the opposite of what we've done, plus a little bit more, but essentially the basis of it is what we would call as anti-differentiation. Alright, so here's the reverse process. The reverse process of differentiation. And so all those patterns we've been using, we just do them in reverse. And of course, on your formula sheet, the common ones are on the formula sheet. So there's two columns. One column is the derivative, and then this column is the antiderivative of your common ones. Okay, so a mathematical way of writing this is if big F dashed x is equal to some other function which I'll call little f, then, now the symbols that we use to anti-differentiate, or to indicate to us to anti-differentiate, is this little, not big, swirly, messy, anti. Yep, it's called the integral sign. And when we get down the track, we'll have numbers on each end of this, but for the moment, we're not. So it's the integral sign, and what it means is anti-differentiate.
So that means that the rest of you are on the car blind here, is that we right? Ready? Yeah. Can you listen? Alright,
so when we see that, it means to anti-differentiate. We're anti-differentiating this little f with respect to x. And what do we get? Well, we get big F, the function big F, not the derivative big F, but the function itself, big F. Now, there may also be a number on the end. So plus c plus some constant. Just remember, if we differentiate, say, the number 5, if we differentiate the number 5, what does it become? 0. So if we haven't got anything there and we anti-differentiate, go back the other way, we're not sure whether there is a number or not. To find out that number, you would need more information. So that's a constant. So often you'll see if we're just anti-differentiating something and we don't have other information, we'll just see plus c on the end. And so we need information to find it. Alright, so let's have a look at some antiderivatives. Alright, we got that? We have. Oops. Okay, so find an antiderivative. On the antiderivative. Alright, so the first one, 6x minus 2 on x squared. Alright, so the same thing that we did before with when we differentiated. Rewrite this first bit here. So we'll rewrite, not the first bit, the second term I should say, as 2 times x to the minus 2. And work from there. And the same if we've got roots, we'll rewrite the roots as index form. Alright, so we want to find the antiderivative, so mathematical way of writing that, integral sign, 6x minus 2x to the minus 2 with respect to x. Alright, so before, when we differentiated, what did we do? When we differentiate a polynomial, differentiated that. What did we do? We brought the power down, decreased it by 1. So the old power came down and multiplied, and we reduced the power by 1. So if we are doing the reverse of that, the 6 would stay there. The power, well, it's got to do the opposite. So if it decreased by 1, when we anti-differentiate, it's got to increase by 1. And over here, we multiplied by the old power. So if we're doing the opposite to that, if we're doing the opposite to multiplying, we are dividing. And the opposite to the old power is the new power. Alright, so when we anti-differentiate, we increase the power by 1 and divide by the new power. Alright, it's written differently to what I've talked about on the formula sheet. So make sure you refer to your formula sheets as you go. Alright, so that's that. Increase the power, minus 2 becomes minus 1, and we divide by the new power. And then plus c. Alright, so when we neaten this up, we end up with 3x squared there. These minuses become a plus. 2 and x to the minus 1, the x goes down the bottom, plus c. Yes? Anything about that? No? All right.
Did you say it's better to write it as 2 over x?
It's probably better to write it as 2 over x, yes, because that's then here it's got a negative index. Generally they prefer positive indexes. So yeah, 2 over x would be the better option. All right. Okay, so this next one we're going to do is B, it's e to 3x plus 4. So we're looking at the integral, or the antiderivative, of e to the 3x plus 4. Alright, so here we've got a little bit of a complication in that our power on our e to the x there, or our e to the power of, it's more than just kx. It's got this plus 4 on the end. So what we do in this particular case, we have a look at that power and we say, okay, so let's let u equal to 3x plus 4. All right, and so then if we differentiate u, we get du dx, and that is 3. All right, now we're going to use these things to help us. So we're going to change e to the 3x plus 4 dx to something involving u rather than. Now, there's a couple of different ways that I could kind of explain this, but if I've replaced this 3x plus 4 as u, then I need to replace this. I need to replace this x, because now we've got something which is written in terms of u, so we've got to work in terms of u. So there's a few different ways I can look at that, but one of them is to rearrange this. And so if I times both sides by dx and divide by 3, you can get that dx equals du over 3. Alright, so now I'll replace that as du over 3. This 3 here is the normal number. Now if we have one of the properties of integrals, if we just have a constant that's multiplying in there, in this case dividing, what we can do is you can take that and put it out the front of that integral. So often that's going to make things a bit more simple for us.
But if that's not a common factor.
Yes, it is. Why is it not a common factor?
Because EU is not over 3. Alright.
And so now we've got e to the u, du. Now when we differentiated, you differentiate e to the x, what do you get? Just e to the x, yeah? And so if I anti-differentiate, again it's got to be e to the x. So if I anti-differentiate e to the u, what do we get? E to the u plus some constant. Now that u was put in there to help us. So I've got to replace that with what it was, which was 3x plus 4 plus c. So another way that we could look at that, and I think this is the way it's written in the formula sheet. Is that the integral of e to the kx dx is 1 on k e to the kx plus c. Alright, so the k in this case is 3x, 3, and here the 3's ended up there. So that's the form that will be written on the formula sheet, I'm pretty sure, from memory. So you can use that, make sure you get the formula sheet handy so that you can refer to them. Alright. Okay. Alright, to rub that the next one, example. I'm going to use a circular function example. And so what we are wanting to anti-differentiate this time is sine 3x minus I on 4. So we're after the integral, sine 3x minus I on 4 dx. So we can use a similar technique that we used in the previous one, because we've got more than just sine kx, we've got this minus pi on 4 bit. So we can say let u equal 3x minus pi on 4, and so du dx would be 3. So from that, if we do that rearrangement a bit like I did before, you can say that dx then would be du over 3. So when we do our integral and we rewrite it in terms of u, it becomes sine u, and dx is du over 3, and then we take that 3 out the front. All right. So let's think about our differentiations then. So if I was to differentiate sine x, what does that become? Cos x. If I differentiate cos x, what does that become? Negative sine. All right, so now think about, we're going back the other way. So here we've got sine and we're going back the other way. So it's this one here that we're working with. And we're coming back the other way. And we're going back to cos. However, what else is involved in this? A negative. Have we got a negative here? No. How can we get around that? So if negative sine goes back to cos, then just straight sine would go back to
Negative cos.
negative cos, exactly, yeah. So let's go back to negative cos. I'll put there's the negative, put it out the front. 1/3 cos u plus some constant, and make my substitution back, which was 3x minus pi on 4. Alright, questions about that one? Alright, that's the one that kind of trips people up. Often forget the negative. You've got to think about we're coming back the other way. And so sometimes people go, oh, it's a sine, oh, that goes straight to cos. Yeah, we go straight to cos when you differentiate, but when you anti-differentiate, it's that second one. So just be careful with that. All right. All right. All good so far? Yes? All right, now there's a thing called a definite integral, and I mentioned that sometimes we can have numbers on the ends here. And so when we have numbers on the ends here, it's a thing called a definite integral. And we can go further steps. This is certainly part of that process of the definite integral, but we can go further. And so now we'll have a look at that. All right, definite integral. So when you see something like this, numbers on the end, a to b of some function with respect to the integral from a to b of the function with respect to x is the definite integral. Whereas previously we were just anti-differentiating, we ended up with a function. It's called a definite integral because we get a particular value. So previously, depending on the value of x, you could get different things. But here you get a particular value. So it's the definite integral of fx between x equals a and x equals b. And the smaller numbers on the bottom and the bigger numbers on the top. What does it represent? Okay, so it represents the area between the curve x-axis and the lines x equals a and x equals b. So if I was to do a rough sketch, then what it represents is that area in there. All right. Okay, how do we deal with it? All right.
So a is always a smaller number?
A is always the smaller number. Always, yes. One way to think about it is when you put in x equals b, you get the area all the way back into the axis.
Yeah.
But we don't want this bit, so we want to take it away. So we're always going that area minus that area in effect, which is what I'm about to start now. All right, so how do we work it out? So how we work it out comes to what's known as the fundamental theorem of calculus. And the fundamental theorem of calculus says this. So from the fundamental theorem of calculus, a to b of little fx is equal to big F when you substitute B in, minus big F when you substitute X equals A in. And big F is the antiderivative of little f. Alright, so that's where the previous bit, the anti-differentiation stuff that we're doing, that's where that comes into it. Alright, so a couple of things, a few things to note. A, one down the bottom here is called the lower limit. B, the one at the top, is called the upper limit. And fx, got a funny name. Called the Integrand. So it's just the function you're anti-differentiating, or the function you're integrating. Not sure that you'll see that last term, this integrand term, used a lot, but put it down just in case. All right. So let's have a...
And integrand is the function that
the function you're integrating or anti-differentiating, or however you want to. Think of that. All right. Can I rub that off? Do some examples. Got a fair bit of stuff today, unfortunately. All right, so let's do some examples of how we might do it. Okay, so evaluate the following. Okay, so first one, 0 to 1, e to the 2x minus x with respect to x. So, fundamental theorem of calculus. So the way we write this out is the following. So we anti-differentiate these things. And so the way we set out is using square brackets, and the antiderivative of these things goes inside the square brackets. So the antiderivative of e to the 2x, when you look at your formula sheet, so if we're anti-differentiating e to the kx, it would be 1 on k e to the kx plus some constant. All right? So 1 on, not k, but on 2. E to the 2x. Negative x, well that's a polynomial, and before what we said, we increase the power by 1 and divide by the new power. Now, of course, there'd be a constant involved with that, and if we've got two constants, put them together. I'll just put them together as one constant. All right, so we then put our limits there and there, and now we do the fundamental theorem of calculus then. So this was our little f, this is now our big F. We've now got to put these numbers in. Now the fundamental theorem of calculus says big F of the top number minus big F of the bottom number. Alright, so the way I do it is, looking at it is like this. So we've got a half e to the 2 times 1 minus 1 squared over 2 plus constant minus half e to the 0 minus 0 squared over 2 plus the constant. Alright, so what have we got? Half e squared minus a half plus the constant minus a half at 0 plus the constant. Got that? I hope. Now, what do you notice about, in this case, about the constant? It does. So when we do an integration, we don't actually even need to worry about writing it out, because we've got plus the constant here minus the constant. So it's effectively going to get rid of itself. So generally when we're doing here, we wouldn't even bother putting it in, because it's going to subtract itself later anyway. Alright, so then what have we got? We've got half e squared. We've got minus a half here, and then minus another half, which is minus 1, I believe. So there is our value of our definite integral.
So is that the area?
So this would represent the area under that graph between x equals 0 and x equals 1. That's what that number represents. Any other questions before I rub that out? Do my next example. All right, next example. All right, to be this time we want the integral between 0 and pi on 8. Yes, pi on 8 of sec squared 2x dx. Alright, so this is where I'd be suggesting you always got your formula sheet handy, so you can have a quick look. You might have a look and you might think yourself sec squared doesn't make any sense to me. However, if you look at your formula sheet, you'll see that sec squared is related to, if we differentiate tan, we get sec squared, don't we? Alright, so always have, be suggesting always have your formula sheet handy so you can just scan and see. So, if we're going to anti-differentiate sec squared, we're going to get tan, aren't we? And we're going to get tan 2x. And this constant here, well, that's going to be 1 over 2, so 1 over the constant. Remember, when we differentiate, that 2 comes out the front and multiplies by the half that's there. Leaves us with the 1. Yes? Maybe?
Yeah.
Yes, thank you. All right. Don't need to write constant in because it's going to subtract from itself later anyway. All right, let's work that out then. So we've got a half tan of 2 times pi on 8 minus half tan of 2 lots of 0. 2 lots of pi on 8 is pi on 4. 2 lots of 0 is 0. Tan of pi on 4. 1, yes. Half times 1 is a half. Tan of 0 is 0 degrees.
1. No, 0.
So that is a half. Anything about that one there? All right, we will now have a look at a different function. So, this exam has 2 parts. All right, the way this question is written is a little bit different, but even if they just had this first bit, the second bit said find that, you'd have to do the first part anyway, all right, because part of the integration process is to find an antiderivative. All right, so first of all, before we look at the second part, we will just look at the anti-differentiation of 1 on 4x plus 2. All right, so 1 over something. So 1 over something is related to what?
Negative 4x plus 2 is 1.
Yes, it is all to the negative 1. What sort of graph is this? Hyperbole kind of graph, yes?
Yeah.
All right. So, with calculus, I've got my formula sheet here with me, but if you have a look at your calculus, the derivative of log to the base e of x is 1 on x, yeah. So that's why I'm saying you have your formula sheet with you so that you can refer to, because you'd be going in there and you'd be having a look at that of something which has got the integral of 1 over, we'll say 1 over x, but it's 1 over something. All right, and so 1 over something is then going to be related to log base e. All right. Now, we've got 4x plus 2, not just x, so we need to do that kind of substitution that I looked at before. So I can, if I let, excuse me, if I let u equal 4x plus 2, and then I differentiate with respect to x, and that's just 4, and so then rearranging that, dx is du over 4, according to u, whichever you prefer. And so now what we're going to do is we're going to change 1 on 4x plus 2 to 1 over u, because the 1 over u bit, we know how to deal with that very easily. But because we've changed it to 1 over u, I need to change the dx to the thing with the u in it. And effectively, I'll put that 4 at the front as a quarter, excuse me, and then I anti-differentiate with respect to u. So if I anti-differentiate 1 over u, that becomes log to the base e. Now, what do we know about the logs, numbers that we can take logs of or can't take logs of? It can't be negative. So, when we're anti-differentiating, because this number, this u, can't be negative, when we're anti-differentiating, we use modulus signs. So we say the modulus of u. Alright, which just means ignore any negatives. Now, this time here, and this is a subtle thing that you need to, when you're reading the question, those very first ones, the questions were worded, find the antiderivative of. See, this one here says find an antiderivative. So when it says an antiderivative, usually you won't see a constant there. Right? So because an antiderivative, well, the constant could be some number. Plus zeros would be an antiderivative, plus 1 would be an antiderivative, and so on. But generally, worded an antiderivative, you don't see any constant written there at all. Alright, so sometimes when you're in your textbook, your questions that you're doing, sometimes they'll have plus C, sometimes they won't. So if they don't, just go back and look at the question, and if it's got the word an antiderivative, that's why they haven't got a plus C there. All right. So now we've found an antiderivative. That was the first part. And so now we're going to use that with this integral. Because we found our antiderivative, so 0 to 1 of 1 on 4x plus 2 dx, inside that square bracket, when we're doing the definite integral, inside that, it's this antiderivative, isn't it? So that's that. And so now we can substitute those numbers. So a quarter log to the base e, 4 times 1 plus 2, minus a quarter base E. 4 times 0 plus 2. So we've got quarter log to the base E of 4 plus 2 of 6. And 6 is a positive number, so I no longer need the modulus signs. Minus 1/4 log to the base E of 2. Now what? Any suggestions? What about this quarter? What do we know about this quarter? It's a common factor, so let's take it out as a common factor. Then I've got log to the base E of 6 minus log to the base E of 2. When we subtract in logs, divide 1/4 log to the base E of 6 over 2, which is 3. So we've got 1/4 log to the base E of 3 as our definite integral.
Can't go to the top.
Sure. All right. Anything there about that? No. All right. Last bit. And one example. Graphs and antiderivatives. Right, so to solve these problems, we think of big F dash is equal to little f. So i.e. big F is the antiderivative of little f. So what does that mean is that the graph of little f the gradient of big F. Alright. So if we're anti-differentiating little f to get big F, and that means that little f is the gradient of big F. Alright, that's the key thing. Alright, so the key thing there is little f. I'll write that down. Another one. So little f is the gradient of big F. So often we're going to be given little f and have to draw big F. So little f tells us about the gradient. All right, one example. Okay. The graph of fx is shown. So here's fx. So there's fx. All right. Here we go. So now we're going to change the way we're thinking about these these graphs. So this graph, when you look at it, this green line looks like a parabola, doesn't it? But now what we've got to do is we've got to think about our y values here. So our y values on here, these numbers here, they're telling us about the gradient. Alright. So they're telling us about the gradient. And in this case, all these y values that correspond to this green line, they're all positive, aren't they? So what this is indicating is that, first of all, the gradient of f is always positive. So we need to think of ourselves, what sort of graph can we have which has got a gradient that's always positive? What sort of graph? Cubic? Would a cubic?
No.
It's not always positive. Would be, wouldn't it? Now, also, think about, we said this looks like a parabola, yeah? When you anti-differentiate something to the power of 2, what does it become? Power of 3, which would be a cubic. All right, so there's two ways heading us to the same kind of conclusion. So if we're going to have a positive gradient, it's going to go something like this. Got something here looks like a squared. Anti-differentiate, increase your power by 1, you get a cubic. So we're thinking we get something that's looking like this. All right. So f dashed x, another way of writing it, f dashed x greater than 0. All right, so we've got a positive gradient on this thing. What else have we got? So we've got a positive gradient, decreasing in value, gets to the lowest value of 2 there, and then increases again. So what do you think that kind of thing is going to indicate? Any ideas? No ideas? Alright, so again here we've got gradient decreasing, then increasing again. What do we call this point? Point of inflection. So here it's indicating a point of inflection is what it's indicating. Alright. Alright, so indicating a point of inflection. So at x equals -1. Indicates a point of inflection. Now, in the mathematical sense, if this green line is our derivative, then f dashed -1 is equal to 2. If you do a second derivative, if you differentiate a number, what do you get? Yeah. So, point of inflection is what that's indicating. All right, and so the gradient is 2. What else have we got? Oh, we've got this one here. So what does this bit tell us about? It tells us about our big F. And when x is 0, y is? So that's indicating that this is going through the origin. Yep. So f0 equals 0. It goes through origin. All right, so let's put a few of those things together then. This is our F, big F. This is our big F. I'm going to use red for big F. All right, let's start with this one here. That's the only one we definitely know. We definitely know it goes to the origin. If you're at -1, so somewhere along this dotted line I've done there, that's where we have a point of inflection, and the gradient of it's always positive. So, where would our point of inflection be? Down here or up here? Down. All right. So I've got a point of inflection, and because the gradient's 2, it's not. No, it's not a stationary point of inflection. It's just a little on an angle point of inflection. So come down here, something like that. And we'd need more information to know precisely how steep and precisely whereabouts it is. But we know it's somewhere along that line. We know it's down there, but precisely where we'd need more information. All right. So that was a bit of a long one today. All right, anything else? There's a fair bit of news, fair bit of stuff to get your head around in that. All right, 7A then.